martingale, a martingale in respective value of, and just one completion on the past, and x naught, and that is equal to times event. So these two random variables are equal, that is a martingale, and what else? It is a super martingale or a sub martingale, respectively. That will be this inequality and the other term. Okay. So today we're discussing section 5.3 on the so the first theorem that we need to mention is, well, so given that definition of the martingale to take respective value of both sides, we have the following. If Mn is either a super or a martingale or a sub-martingale, here, then we would have the following direction of the respective value of Mn is, so either is less than, equal to, or the other way, compared with respective value of Mn. This could be seen by taking the respective value of that equation, the recalling function. So expected value of y condition on x is expected value of x. Right? That's right. Expected value of y on x. Okay. All right. Yeah. So this is pretty straightforward, I would say, straightforward from the definition. Taking expected value on both sides of martingale definition. So we get all we need. Alright, so when you move on to definition 2, so this is a definition, just a rigorous version of the so-called stopping time that you have seen. So a random variable t taking values in the set of integer and also could take infinite. If it's called a stopping time with respect to collection of a 10. All right. If the following, if the indicator function as a random variable event t is equal to a is adapted to the collection of, so let me call this notation, vector adapted to, right. So if you have this indicator function as a random variable is adapted to this past, then you call t being the stop. So if you still remember back in the day when you learned stopping time in chapter 1, a stopping time means the event t is equal to n can be determined based on the past, and this is exactly the regress version of it. So we mark. Alright. So number one. So this is a regress, say, definition of the stopping time in chapter 1. Okay. See this? See this? Recalling back in the day, you learned like this, so the event T, V, and N. All right. This event can be determined. Sorry, I should say the occurrence. That's my eraser. So the event, the occurrence of the event T, V, and N, right, can be determined based on the past x and x naught. So what does it mean when I say being determined? Basically, that means, so for instance, if this occurs, that means this. So for instance, here, let's say T, V, and N definitely occurs given a collection of the past, A of B, x and real x n, x naught to real x naught. That is the same thing, is the same as the indicator function 1, T, V, and N. Conditions on AB is identically 1, a constant. Okay. I think I got it. Right. So if such an event occurs here in the past, it's the same as saying that indicate a random variable condition dot AV is 1, just a constant. In other words, that random variable is adapted to the collection from x naught to x n. Okay. On the other hand, suppose if this does not occur, is the same as this indicator function condition on AV is 0. So that's it, right? So that's why we call it is adapted. So the mark number 2 is as a consequence of the as a consequence of the definition. All right. If t is a stopping time, then so t is a stopping time. Then 1 over t greater than n, 1 over t less than n, or both adapted to x n. Good fact. Now this is something I'm sure you have seen over. Something you have employed before, but here we have rigorous terminology. So you see this? You observe the indicator function t less than n. All right. So that random variable can be composed goes into a summation. One indicate function t in k. K, let's say from 0 to infinity. Right? And so as you can see, if I give you, let's say, a condition on a trajectory a sub v, then every one of them here is a constant. So the sum is a constant. So one condition on t less than n. This random variable condition on av is the same as the summation of one t in k. Condition on av. All right. And this is a constant. A constant. So basically, it's either 1 or 0, basically. I mean, we're saying constant sounds kind of fancy, but either 0 or 1. And so the sum is a constant, basically. So if the sum is a constant, in other words, this random variable conditioned on AV is a constant. Is a constant. In other words, this random variable is adapted to Jackson. Apply one t less than n, adapt to function of fast. Similarly, so say similarly, this indicator function as a random variable put it in n. This is just simply 1 minus 1 t less than n t. So as you can see, the other two random variables are adapted. So this has to be adapted. Use that. Okay. All right. So now let me move on to the first nice theorem of this section. This is a theorem I believe defined for the third thing in this book. So if t is a stopping time together with mn is a vertical. Right? The conclusion is expected value of m t mean n is equal to expected value of m. We're calling the wedge notation is just the minimum. So here, notation t wedge n is simply the minimum between and right. So this is kind of like a generalized version of the previous theorem. In the previous theorem, we have a deterministic index, but here we also have a random index. Have a random index. So generalized version. So let me put it up here. So we have Martin Gans, so command is expected value of n. T min n is expected value of m naught. Okay. Right. So to save time, let me just I will come back to the proof if I have time, but I'd rather go to the application. All right. So just to save time, so if I will come back if I have time. Otherwise, I will just refer to the textbook. Theorem 4. I believe this is theorem 14. So saying so under the pretty much the same conditions, if t is a stopping time and mn is a martingale, just that we have the following. So I know t is finite for sure, and I know there exists a constant, fixed constant k, just that I know that n t min n is less than k. So this is also for sure. All right. Then the conclusion is then something of t is so this is even a lower powerful theorem. So as you can see from the previous theorem, if I have no condition at all, then the best thing I can do is to just truncate t with a fixed constant index. But now if I assume further, then we can get rid of the index. Okay. So again, so for this proof here, I guess I can only refer see the lecture notes that I will post later on. Okay. Or you can read the textbook. Okay. So, but let me just put it up here. So we have something to science back. So if we have if I know t is finite and just mean n is less than k for all n, then the conclusion is that the value of t is not. Alright. And so of course it kind of funky of this condition, kind of funky. And how do we check that? And let me just discuss the following example to see the application of these theorems. Let me consider the symmetric random walk example. So symmetric random walk. I suppose I have again I have a sequence of x and b in Bernoulli taken either 1 with probability 1/2 or -1 with 1/2. Alright, consider S naught being 0 and S of n is summation of x k. K from 1 to n. Right? And so S of n is just a Markov chain. A Markov chain jumping on the integer set. So this is 0, 1, -1, -2, 2, right? So I will start from 0, keep jumping back and forth, basically. And so now, suppose I have to vary some, so consider the following. So settings 0, 1, negative 2. Let's say this is negative A. Let's say this is B, and I start from time 0, right? So that's not be 0, all right? So the question here is, the first one is the probability of, okay, I'm sorry, I forgot to define what stopping time. So define T, at the first time we hit the battery. So S and is either negative A or B, alright? So the first time I hit the barrel, starting from time 0, starting from 0, the first time I hit either negative A or B, and so I want to know the following is equal to negative A, right? So what is the probability I will hit negative A before I hit B, right? Second, expected value of T. I mean, so back in the day in chapter 1, I'm pretty sure you guys know how to do this. I'm pretty sure. It's just, this is kind of like, basically, this is kind of like probability starting from time 0, B negative A is less than B. Basically, something you can do, one-step analysis. This is pretty much the same thing, pretty much similarly. Right, this is expected value of B, you know, B, A, B. You have a sequence of, you have a system of linear equation. And you can solve for this in principle. But here, let me provide a new approach using stopping time here for line here. All right, so see this, step 1. Step 1. The claim is Sn is indeed a Martingale. This is not really difficult to check. This is not difficult to check because I think we already did that, I believe. But let me do that again here. So I just have to prove okay, S of n plus 1 conditioned on Xn. Alright. So this can be written as expected value of Xn plus 1 plus S of n conditioned on S. Alright. And then linear combination, I can split. So expected value of Xn plus 1 conditioned on S plus expected value of Sn. And so this Xn plus 1 is independent of the past. So this random variable is just a constant, which is expected value of Xn plus 1. Let me recall here. Let me recall. If y independent of x, then this random variable is just expected value of y. If w adapted to x, then what do I say? Expected value of w conditioned on x, just w. Right? And so, using those two properties, we know the first term is simply expected value of Xn plus 1. Xn plus 1 plus the other random variable being just Sn. And well, the meaning of this is simply 0 because taking either one or negative one with equal probability. So the mean is 0. So it's just
Again, this is exactly value less than plus 1. Each one passed.
right. So that is step 1. Okay. Any questions about this? Okay. Step 2 is another martingale. I call n squared minus n is a martingale. Alright. And so, couple of ways to check this. Couple of ways to check that. One direct way is to employ just using the definition. Another way is just to recall the example from last time, recall the function f xn, alright? Is, so suppose I consider this function, alright? If, so recall this function, right? If I have f of xn is equal to the summation of the transition matrix Pxy, Fy, n plus 1 for all y in the state space, then what do I have? Then so if then I have f of xn is a martingale, right? So martingale. I guess to say xn because here I have Markov chain. Right. So all we have to do is check whether this function little f in this form satisfies this equality. Then the conclusion is f evaluated at x of n is a martingale, which is this. So all we have to do is to verify this. All right. But it shouldn't be difficult, actually. Shouldn't be difficult. To see this, well, so suppose I am at location x. Maybe let me consider the right hand side. Summation of y in S, f x, p, x, y, f, y, and plus 1. Alright? So suppose I am at the location x, where I can go next? Or x minus 1, right? So either the right or the left, basically. So either I go to the right, so that will be 1/2, with probably 1/2, f of x plus 1, or I go to the left, x minus 1, and this is 1/2. I plug it in, that will be x plus 1 squared minus n plus 1 plus 1/2 x minus 1 squared minus n plus 1. Alright? And so by algebra, this is exactly equal to x squared minus n, which is f of xn. Okay. This algebra over here shouldn't be difficult for you guys. See this. So anyways, the conclusion is, so the conclusion, f evaluated at the Markov chain, and which is Sn squared minus n, is a martingale. Alright? Yes, sir.
Fxn is this one is convex function x squared. Is that
Is that a convex function?
Is this a convex function?
Well, the thing is, it does depend. I have two arguments. So the x and the n.
And also it's a variable.
And so if you fix the n, then just it is a convex function. If you fix n, of course, but if you don't, but I would leave as a two-dimensional function in 3D. I'm tempted to say yes, it is a convex function. Like if you have, but it doesn't really matter here. I don't see convexity having anything to do. Anyway, so we have two important variables in the xn and the xn squared minus 3. Alright. So what next? So the next thing I want to say is so I want to invoke this random. So step 3. So step 3 is I want to show this stopping time is finite for sure. Okay. So I just really knock this step here, it's too fast. The next step is the observation. This is by the maximum of n. Right. If you think about it, so t wet or t mean n, right? Think about it. Okay, so from here, negative a, b. So where is the location that I can be of this random variable? T mean n. That means I have not really reached the boundary yet. I am still inside of this interval. Alright? And so that's why the absolute value of this is trapped between A and B, the maximum between A and B. Right. This is clear. This is clear. Since we already know t mean n, this index here random is less than t, and so s t mean n is still inside of the interval from minus a to b. All right. Okay. I have not escaped the interval because I only escape up starting from time t. I may get outside, but for that I have to be inside. So hence, s t mean n is for sure trapped between the maximum maximum of my t value. Okay. I hope that is clear. Yeah. So that is that. So now step 4 is the following. Now step 4 is following. T is finite. Alright. So this is actually harder. We have to use the other. We have to invoke the fact that s squared sub n minus n is 1 here. Alright. Since from step 2, right, we know s n squared minus n is 1 here. Right. We have a special value of s t mean n squared minus t mean n. Alright. Is equal to special value of, well, s not squared minus 0. that is the first theorem above there, T mean n, right? And of course, this is 0. So in other words, what do I have? So I have specific value of T mean n as a random variable. This is equal to as T mean n squared. Alright. Okay. But what do I know about this? What is the maximum value of that random variable? We know this from step 3. This the square is always trapped by the maximum of a squared and b squared. Right? From step 3. Step 3. And so the expected value of this is always trapped by the maximum of a squared and b squared. Okay. All right. So far so good? Okay, so now how do I get this? Right? In other words, I have to show that probability is 1. Probability T being finite is 1. That is equivalent to say probability of T being infinite is 0. That's all I have to show. Okay, so what do I have? So now I'm going to do this. So note that, okay, so I have what so far? B squared is greater than, it's like the value of T mean n, alright? 1. But this can be found from below by T mean n with the event that T is greater than n. Yeah? Basically, I just decompose the mean into smaller events, basically. I mean, well, of course, expected value of, let's say, z is either z greater than n plus mean of z with z less than n. That is the same thing as this indicator function. See this plus expected value of z or z less than n. Basically the same thing. Okay. And because I know this is because Z, I know this is always non-negative, so I can get rid of, let's say this part first. Let's say. Okay. And then, well, if I already know T is greater than N, then the minimum of them is simply N. T mean N is N because of this. Okay. So that is equal to the expected value of N T greater than N. But then, well, N is just a fixed number. So that will go outside. So N, expected value of basically the indicator function, well, that's just probability of T greater than N. Right. Because you can think about this as the indicator function N times 1, T greater than N. And well, expected value of the indicator of a Bernoulli is just probability of the success, basically. So what do I have? So I have a maximum, a finite number is always greater than n times this. So you divide by n, right? So that would imply that maximum divided by n is greater than probability of t mean n. So if I take n to infinity, the left hand side going to 0 and the right hand side going to t being infinite. I said the probability t being infinite is 0. Right. So take n to infinity. So the left hand side going to 0 greater than the right hand side going to probability t being infinite. So in other words, t being infinite is 0 or t less than infinite is 1. Okay? Yeah? Alright. So now so that is step 4. Alright. The step 4 is that. So now step 5 is to evaluate probability as as t near negative a is what, right? So now, so what do I have so far? So I have Sn is in one again. T is finite for short, and I know St mean n is only trapped by the maximum of A and B, right? So then I can invoke that theorem. So I know expected value of S at T is equal to expected value of S0, which is 0. Alright. But then what is the mean of ST? So at this stopping time, either I am at this location or I am at that location, either negative A or B. So in fact, this is just this is simply so I'll make it quick here. So remember, so ST is either negative A or B. So I don't know that yet. So this probability is, let's say, a probability, say P, for P to be determined. Right? To be determined, and I want to know that. But then you plug it in, right? So the mean of ST is either negative A times that probability plus B times 1 minus P. And I know it is 0. Okay? And so now you can solve by algebra. So by algebra, the P, which is the probability, ST is negative A, it is just B over A plus B. I'm pretty sure not